Okay. So we're going to move on to a series of talks by Ben and then Jim about what this is. I think this is more of the speculative early thoughts on what this event is telling us, possibly about the equation of state of neutrons. So Ben, let's start off.
So I'm lucky that I'm speaking later on in the day, so I'll have much less introduction to do in terms of the modeling of Koganov and what we saw. I think Brian is absolutely right in the sense that when you listen to what I'm going to be saying now, you should take as a general caveat that this is all very preliminary. Everything's put together fastly, and these are sort of your initial thoughts and takes on what we can get from this event. But I think nonetheless it shows that we can get a lot of information, surprising amount of information from this just single event. Okay, so that's just a brief outline of what we'll go through. We'll try to do this faster than the allotted time because there really is no reason for me to take all this time. So to remind you guys, what are the possible outcomes of the merger of two different stars? Just broadly categorizing them. You can either have a stable neutron star, a supermassive neutron star, which is a rotationally supported neutron star. So it's a neutron star that is more massive than what would be supported by a non-rotating state. But this is rigidly rotating. It's essentially a solid body rotator. You can even go to higher masses, essentially have more rotational support if you allow differential rotation. This is a hypermassive neutron star. And then finally, at some point, you can just no longer support anything even with maximum rotation, and you can just get a black hole. So this is sort of, categorizing these, and essentially these are just mass cuts. It depends on how much mass you have and the equation of state. So where these different lines fall depend on the equation of state, and that's sort of the crux of everything here. Another important point is that all of these different merger outcomes have been shown to have qualitatively different electromagnetic counterparts, and that's something that will. Okay, so this cartoon that we've seen before, sort of a nice picture to get these different categories. So what are the different electromagnetic counterparts, roughly speaking, that we can get dependent on the outcome? So if you get a prompt collapse, then what we expect is not a very massive disk surrounding the black hole. So you'd expect not very massive kilonova outflows or ejecta, and velocities from the disk winds, which Daniel mentioned, are of order 0.1 c. So you can't really get, or it's not easy to explain this early blue fast kilonova emission. So on those grounds, sort of, I will, for the rest of the talk, rule out the prompt collapse scenario for this event. What else can you get? So if you have a hypermassive neutron star or a short-lived supermassive neutron star, which are sort of differentiated between the top and bottom of this plot. So this is a long-lived remnant, longer-lived, I should say, and this is a shorter-lived remnant. You can have these two scenarios. So in the tidal tails, the dynamical ejecta, as David mentioned from the simulations, you get, of order 10 to the minus 4 to 10 to the minus 2 solar mass of ejecta at velocities of 0.2 or 0.3 c. This happens in either case in all of these panels. But what difference you have here is that you have a more massive disk. And so you get more disk winds and you get more massive disk wind ejecta. And this disk wind ejecta can either be red if the remnant is short-lived, or it can be bluer due to neutrino radiation that changes the composition, essentially changes the YE fraction if the remnant is longer-lived. In addition to that, because you have two neutron stars, you have, in this case, you also have this dynamical ejecta from the shocked interface between the two neutron stars, which presumably gives you this blue fast kilonova. And the last option that you can have is you can have a long-lived remnant, sort of either an indefinitely stable regular neutron star or a supermassive neutron star that spins down on very long timescales, whatever you want, dependent on the magnetic field that gives rise to this magnetic spin down. And in that case, what would happen is that you would essentially dump a huge amount of energy from this rotational energy of the remnant into the surrounding ejecta, and all of your outflows here, all of the ejecta, will be boosted to relativistic velocities. That's a huge difference. And this, again, is not seen in the observations, so this will essentially be ruled out for the purposes of this talk.
Could you be concrete about what's long and short?
Yes. So, well, I guess for the purposes of the energy injection, what really matters is how much rotational energy you inject, which is something I'll talk about a bit in a second. So that could be even on short time scales. The main difference here in discerning between long and short between these two scenarios is whether you have enough neutrino radiation to change the composition of the disciplines. Maybe Daniel or David could.
It's basically comparing
yes.
the light time to the viscous or accretion time
Yeah.
of the torus. So it's sort of 100 milliseconds. You know, if it survives for hundreds of milliseconds, it's going to make a blue wind mostly, and if it collapses faster, it's going to be more red. But we're still at the quantitative level of figuring out that
helpful,
transition.
thanks.
But it's of order hundreds of milliseconds.
Mhm.
Let's say.
And these are roughly the different mass cuts to get these different scenarios. So, so as I said, this is sort of what we envision as our model for this event, this gravitational wave 17. And what does this mean? So more into this input of rotational energy to the surrounding environment. If you have a rapidly spinning neutron star, as you would have after the merger of two neutron stars, essentially the argument is a simple angular momentum argument. The orbital angular momentum at merger is much larger than the rotation, maximal rotation of a neutron star remnant at breakup. So this thing should be breaking at or very close to breakup. And
Breakup doesn't have a meaning unless it's uniformly rotated.
Yes, I'm talking about a uniform rotation.
Yeah.
Yes, certainly. So I'm talking about timescales after differential rotation has been removed. We believe that initially at merger you get this sort of hypermassive neutron star picture, at least very fast initially, but then differential rotation is removed to angular momentum transport. Correct. So you have a huge energy reservoir, and that's the main point, of order 10 to the 53 erg. So you can see this plot over here. This is the rotational energy as a function of the mass of the neutron star. This is the maximal, essentially, rotational energy at breakup. And it just increases as you increase the mass. But a point to note is that once you get above this maximal mass for a non-rotating neutron star, essentially this is where the supermassive neutron star sits, the amount of extractable energy starts dropping as well. And the reason is that although you can have more rotational energy in the rotating remnant, once it collapses, at collapse, a lot of this rotational energy essentially will be swallowed into the black hole, just go to the black hole spin. So you can extract less of it. And so if this essentially energy reservoir will be tapped by spin down, we believe that it will be tapped by magnetic dipole spin down, essentially going into some sort of electromagnetic counterpart, which I'll discuss in a bit. The other alternative, which one could envision, is essentially a gravitational wave that just spin down. So people in the audience like Simone have worked a lot on this. But in this case, we believe this is not a likely scenario. So if you just look at this plot, this is magnetic field. This is the external dipole field and internal toroidal field of the remnant. And you can see contours of where the electromagnetic spin down equals the gravitational wave spin down energy. So in this region, gravitational waves dominate, but everywhere else, essentially electromagnetic spin down dominates. And you see that this region, first of all, sits at very high toroidal to colloidal field ratios, which are thought to be unstable. This is work by John Brayfight and others. Additionally, the time scale for collapse, or for spin down, I should say, in this regime is of order hundreds of seconds, which may be incompatible with the GRB delay of 1.7 seconds, depending on your GRB model. And additionally, it was not detected by LIGO searches after the merger, which is something that I'd actually be interested to hear more about from the LIGO people, because this is sort of not very, he mentioned this in the PRL paper, but it's not very well described. So it's interesting what these constraints actually tell us. Yep?
On the gravitational wave spin down, what is the quadrupole moment?
Okay, so yes, I should have mentioned, the quadrupole moment here is induced by electricity caused by the toroidal magnetic field.
But you also have the classic Jacobi ellipsoid instability for the differentially rotating case, which gives you a quadrupole moment and gravitational radiation.
Well, these are not differentially rotating. These
Oh,
are,
okay.
yeah, these are
But for the differentially rotating
self-bodied.
ones,
Yeah, I haven't looked into that, but these, I'm assuming here are solid.
Well, the ratio of the kinetic to gravitational energy is about 14%.
Oh yes, so we're below that. Yes, in that sense, yeah.
In the differentially rotating case.
In our, so we don't construct differentially rotating models, but in our solid body models, the ratio of rotational to gravitational energy is below this condition of 14%.
So it is below 14%.
Yes.
We may start out above it, but eventually it'll spin down and it'll be below it.
Yeah. For the equilibrium ones that we.
And it still has a huge amount of rotational energy, even once
Exactly.
it's spin.
The only question is,
Has anyone made
do you
differential
really need
rotating
the object to survive for less than 2 seconds?
For the GRB.
Yeah.
Well, it depends on your model, right? So the two sort of, I'm sure there are many people who can comment more on that, but the two models that at least I have in my head are, the options are either you form a black hole and the GRB is powered by accretion, and then you need it to go for 2 seconds, or alternatively you power it by spin down of a magnetar, but then also you need the spin down time scale to be sort of comparable to the GRB time scale, otherwise you don't get any energy in the spin down. So in both cases, I think you need to spin down, not necessarily collapse, but at least spin down in time scale of 2 seconds.
And I mean, you also have a quadrupole, not just a quadrupole moment from the toroidal magnetic fields, but also these merger remnants are non-axisymmetric at the beginning. So it's certainly right that you have like a very high energy reservoir, like at the time of merger, so of 10 to the 53 but still these are very distorted objects that actually can radiate away quite a fraction of this in gravitational waves. So
on what time
once
scale?
on milliseconds, so tens of milliseconds time scale.
I guess the question is whether this time scale is longer or shorter than the time to remove differential rotation, right? Because all of these axisymmetric instabilities will sort of be smoothed away once you remove differential.
But these are
rotation.
very fast, so the gravitational waves are pretty fast. So these are millisecond timescales, and we can remove quite a bit of rotational energy by that.
Okay. Well, yeah, that's something that definitely, in this simplistic model we can't capture, but it's very interesting to see what merger simulations find. I know.
Yeah, to evade the constraints we're talking about, you'd have to radiate like 90%.
Yeah, you'd have to radiate such a huge amount of energy, and if you radiate it on time scales of milliseconds, I think that would be a huge gravitational wave in luminosity. I don't know if LIGO could put constraints on that, but it sounds like a huge luminosity. No. Okay.
No. I was just thinking that if they lose all 90% of their spin energy in milliseconds, but I don't know if they can see the millisecond signal, but it would be very
It's
powerful.
an incredible burst of gravitational waves,
we
right?
have a remnant paper which apparently is not out yet.
Okay.
Okay, because they mentioned it's not seen, but we cannot rule out.
We are not seeing anything.
To know more
And
about that.
I actually mentioned at the beginning that I'm not sure we're going to see anything, even with events like with sensitivity, unless we ever goes by orbits.
Yeah, this is most
It's
likely.
just those higher frequencies, we're not there, and
Yeah, I guess the question is you don't see anything, but the null detection is still important in the sense that you might be able to rule out sort of the scenario that Daniel was describing. Maybe, I don't know.
Yeah, I mean, I'm sure there would be certain models which can be ruled out if the amplitudes are very high at those frequencies, and then we are searching. Yeah. We're never going to search anything above probably 3-4 hertz. So this is the 1 to 10 hertz it's quite search which we have been doing now, but there's nothing. And short and longer remnants, that's as well, I guess. If it come out, I'm surprised it's not out yet.
So the paper is not out yet, but it would be.
It's brilliant, I've seen it.
Okay.
Okay.
It's good to know the upper limit.
Yes, exactly. Johan?
Let's get up to this up.
Yeah, it's sort of a simple question.
No, there is in the main paper subjects where I'm telling you. There is in the main paper there is like 3 lines on it.
Yeah, but
Yeah, there's a reference to it, but there's like
That is no paper.
I can't find it.
yeah, so more, let's say.
Yeah, indeed.
It's just a second.
Unless they discovered something which I don't know. Because it's being
But if you remove, then it's very early, and that's before spin kicks in. So.
Yeah.
Yes.
That's,
The maximum.
so then you don't.
But
Right.
just pick out that
Can we
Only one person speaking at the same
they
time.
say we cannot rule
So Joe had a very good question at the back about thermal pressure. So these remnants, as he mentioned very correctly, are cold when they merge, but after merger they're very hot, and thermal support is actually something that can be very important, especially initially, the Kelvin hold size till whatever seconds or whatever it is. So this is something that is not accounted for in our construction of equations of neutron star models, but I'll maybe get back to it later. I will argue that it actually would give stronger constraints than what we find without thermal support. I'll try to, if I don't get back to it later, then remind me. Yes.
Just to comment on what was said before, what you'd expect from Chandrasekhar's old work, and the same thing that was done with compressible stars, is that you go into a triaxial shape and radiate gravitational waves, and then when you got down to T over W of about 0.14, it would be spheroidal and differentially rotating. And I would imagine that's what would happen in your simulations if you just did this hydro solution. And that would give you a high frequency signal, which I guess LIGO hasn't seen.
Yeah, we'll have to wait for the paper,
trouble with
but
high
yeah.
frequencies, that's the problem.
Yeah.
You know, because you have a rotating bar for a long time.
Any comments, questions, additional? Okay. Yes, where was I? Okay, yeah, so I was talking about this huge energy reservoir of 10 to the 53 ergs of rotation that's essentially tapped by electromagnetic spin down. And this spin down, or at least, dumping this amount of energy into the surrounding environment, the ejecta, is essentially inconsistent with what we see with the kilonova and GRB energetics. So if you look at the same sort of plot of the maximal rotational energy or extractable rotational energy as a function of mass, these are, by the way, the sort of divisions between stable neutron stars, supermassive neutron star, differentially rotating hypermassive neutron star, and a black hole. Then this is sort of the inferred energetics of the GRB plus kilonova of order 10 to the 51 ergs. So if you need to be in this region, you really have to be to the right of where this blue line intersects the red line. Otherwise, it's just inevitable, at least in my opinion, that you will dump a huge amount of energy into the surroundings, which is not what we see. And that's sort of the main point of our argument. Okay, so once we have that, we can go to what we're actually interested in, and that is the consistency of different equation states. So this is the plot that we've seen before, this nice posterior distribution of M1 and M2, the different masses, component masses of the emerging neutron stars. And what you can do is use this inferred probability distribution and construct a probability distribution of remnant mass given an equation of state. So what you do is for each equation of state, essentially you have a conversion between gravitational and baryonic masses. There are subtle differences, not too large, but tiny differences, depending on the equation of state. And sort of a line of constant baryonic mass is, one of these dashed lines, for instance, is just a schematic, not exact. And if you sum up all the contributions along one of these lines, you can get the cumulative distribution of the remnant baryonic mass. And that's one of the key quantities that we're interested in. So what do? What's our process? Essentially, we construct an equation of state, just choose a random equation of state, choose a bunch of those. We build a rotating neutron star using this RNS code. What do I mean by that? Essentially, I can construct models of neutron stars rotating at breakup, non-rotating neutron stars, and neutron stars that have their maximal mass. So essentially, get all of this information. Essentially, from that, I can get the maximal extractable rotational energy to get this curve. As well as where all of these different divisions sit. So where the neutron star maximal mass is, where the transition between the supermassive to hypermassive neutron star is. All of that essentially is information that comes out of building these static configurations. We can also get the probability distribution of the remnant mass, as I just described. And then the last thing is you can sort of calculate this consistency, which is essentially the integral over the probability distribution of the remnant baryonic mass over the allowed region. So this gray here, which you can barely see, is this probability distribution of the remnant baryonic mass, and the consistency for a particular equation of state. And the consistency of this equation of state is essentially the integral over that probability distribution in this allowed region, which is just this tiny tail, which you can barely see, which is why this equation of state is only 4% consistent, which essentially is zero. It's sort of because these probability distributions are so narrow, because we have such a good handle on the chirp mass, essentially this is sort of a binary thing. It's either consistent or it isn't. You very rarely get a condition where something is sort of marginally consistent. And that's sort of the process of what we do. And with that, we can do this for a bunch of different equation of states, sort of a survey, if you will. Though it's sort of hard to define what a surveying equation of state parameter space actually is. I certainly won't claim that this is, comprehensive or that I scavenge the entire parameter space of equation of states, because there is no such thing. But at least for the equation of states that we looked at, the circles are sort of these named, known microphysical models for equation of state. The triangles are just other equation of states that I randomly constructed to fill in this plot more nicely. What you can just see by eye, so this is a plot of radius of a neutron star. This is a 1.3 solar mass neutron star versus the maximal gravitational mass of a neutron star. These are known pulsar masses, or neutron star masses measured in our galaxy with error bars. So this is the famous Antoniades pulsar, which has the 2.01 solar mass. So we know that the maximal gravitational mass of neutron stars, non-rotating neutron stars, is to the right of this. But we don't really have a strict upper limit. We don't really know where the maximal mass actually is. So the colors here, the encoding of the colors is the consistency. And what you can just see very easily by eye is that stiff equation of states, namely equation of states that have a large maximal mass, are not consistent with our observations, whereas low maximal mass is consistent. And so you can sort of use these consistency points as points on a probability distribution, get the cumulative probability distribution, which is this shaded gray line in the background, and what you find is that you can put an upper limit on the maximal gravitational mass of a non-rotating neutron star at about 2.2-ish, 2.17 solar mass.
If you allowed for differential rotation, would it change it a lot?
Well, differential rotation is completely different. So our whole conclusion is based on the fact that we assume that the remnant is differentially
I
rotating
understand
and
that.
not.
But if you allowed for the other, would it make a big change or a small change?
Well, what do you mean by, I guess I'm confused, but what do you mean by allow? I allow for, in the sense of what this event gave rise to, I only allow for differential rotation. I rule out the prompt collapse, and I rule out the long-lived remnant, right? If we look back at this picture here, sort of I rule out this scenario and I rule out this scenario, so I'm only allowing for this differential rotation. What I'm doing is constructing models of non-differential, rigidly rotating models in order to exclude this, but essentially the argument is that this is what we saw. We only saw differentially rotating neutron star. Maybe we can talk offline. So this is sort of the main plot. You can also, get a back of the envelope estimate for this if you want. Just take a simple analytic estimate for the conversion between baryonic and gravitational masses, from which you find that for the parameters of the GW 170817, the remnant mass is about less than 3.06 solar mass. If you assume that the transition between the supermassive neutron star to the hypermassive neutron star occurs at about 20% above the maximal mass of a non-rotating neutron star, which is what we find roughly for all of these equation of state. Again, this is not the analysis that we do, but this is just back of the envelope estimate to see where this comes from. Then the requirement that the remnant mass is larger than the maximal supported supermassive neutron star mass just gives you this sort of see where this comes from. Okay. So that was our work, and I'll briefly, just in a minute or two, mention some other constraints on the neutron star equation of state, most of which have actually been mentioned before. So this is this tidal deformability, which we've seen this morning. This is this parameter, which essentially has to do with the induced quadrupole moment in the neutron star. And from the constraints that I read off the PRL LIGO paper, I can quickly invert this and get that the 1.4 solar mass radius is less than about somewhere between 12 and 15 kilometers, depending on your assumption for this love number. Additionally, something that Matt just mentioned. So if you assume that the large blue kilonova ejecta that we saw with fast velocities comes from or originates from this shocked interface, then that also points to a very small or compact neutron star, just from the fact that to get these large velocities, you need a deeper potential well or a higher impact collision. And then a last sort of constraint that was recently appeared on the archive as well is the constraints from lack of prompt collapse. And so these are essentially sort of scaling relations found from simulations, merger simulations by Gauss-Stein. And if you use those plus the condition of causality, then you find that the 1.6 solar mass neutron star radius should be above 10 point something kilometers. So putting this all together, and sort of my summary slide, if you look at this nice plot that we all know of mass radius relationship for neutron stars from the review paper by Oswald Fair, then you can add these constraints that I've just mentioned. So this is this Gauss-Stein constraint on the 1.6 solar mass neutron star. So this is sort of ruled out by their law constraint. This is the constraints from the tidal deformability, roughly. Again, just an illustration. And this is sort of the constraints that we find on the maximal mass. You can start punching in on this, or eating up from this plot and ruling out lots of equation states. And sort of my main takeaway is that I guess multi-messenger is not just a code name. It's not just something that you can flash. The multi-messenger science is actually here, and I'd like to emphasize the fact that this sort of analysis couldn't have been done just based on the gravitational wave signal or just based on the electromagnetic observations. It really needs both. Without both of them, you couldn't have done any of this. So this is multi-messenger science. The other thing is that you get really strong inferences just from a single event, which was kind of surprising when I first did this. I'd been hearing and thought initially that in order to get constraints in the equation of state, you need to sort of pack up, pile up statistics, get a large number of events. But it turns out that with a large SNR event, you can get a lot of things because it is multi-messenger. And just for the future, that future events may probe different regimes. So example, if you had a much larger total binary mass instead of this 2.74 solar mass for this event, you could probe a regime of prompt collapse and place actually a lower limit on n max that is larger than maybe this 2.01 solar mass that we already know from the galactic pulsar. So that's for the future. And thanks.
Questions? Additional ones? So everyone got them out of the way during the talk itself. So let's thank Ben again. We're going to hear from Jim, possibly some